Okay, welcome back everybody to part 2, actually part 3 of this video. In the previous video we found out the equilibrium concentrations of magnesium ions and fluorine ions, right? And for this video we are asked to find what is the molar solubility of magnesium fluoride, how many grams of this magnesium fluoride dissolves. Dissolves, I don't know why I put dissolves in 1 liter of water. Okay, we're assuming water. So let's get started with this video. Okay, and this video, this part right here and all these calculations is somewhat based on the calculations we figured out from the last part. So in the last video we figured out that at equilibrium the magnesium concentration, the Mg2 plus concentration, which was equal to X, was equal to, let's see what it was, let's see, hold on 1 second, 2.4 times 10 to the negative 4, okay? That was the concentration of magnesium, molar. That was the concentration of magnesium at equilibrium. And now the concentration of fluorine, okay, which was 2F minus, which was equal to 2X at equilibrium, okay? And actually let's write this: magnesium and fluorine ions, right? Since fluorine was 2x, right, because the fluorine had a 2 in front of it, it will be 2 times that, so I would say it was 4.7 or 4.8 times 10 to the negative 4 molar. Okay, so now this is specifically tied to the molar solubility, and what the molar solubility is asking. Okay, so if we go back to our handy reaction, which was magnesium fluoride solid, okay, generates magnesium ions, which is Mg2 plus aqueous, plus 2 fluorine minus aqueous. This reaction tells us the answer. Okay, it says for every magnesium fluoride, for every magnesium fluoride that dissolves and breaks up into its substituents, right, we generate 1 magnesium and 2 fluorines, right? So now let's reverse that a little bit. So for every magnesium we generated, how much magnesium fluoride did we have to dissolve? Well, that means that we had to dissolve 1 magnesium fluoride to generate 1 magnesium, right? So that's completely tied. So the concentration of magnesium is specifically tied to the concentration or the molar solubility of magnesium fluoride. Okay, again, the molar solubility, what it is asking you how much of the solid dissolved. Okay, so we figured out that the magnesium fluoride concentration at equilibrium was 2.4 times 10 to the negative 4 molar. So in order to generate 2.4 times 10 to the negative 4 magnesium ions, okay, we had to dissolve 2.4 times 10 to the negative 4 magnesium fluoride, that compound. Okay, we needed 2.4 times 10 to the negative 4 magnesium fluoride molecules or compounds. Okay, so whenever you're dealing with a molar solubility problem, and that's one of the questions, and it's asking you what is the molar solubility of a certain compound. The molar solubility is always tied to the substituent that has a coefficient, a stoichiometry, for when you're balancing this for stoichiometry, right, as a coefficient of 1. Okay, so whenever you're trying to figure out the molar solubility, look at your reaction. Okay, look at your reaction. Whichever product, okay, the product, which is your ions, that has a 1 in front of it, a coefficient of 1, that is specifically tied to the molar solubility. So we figured out that at equilibrium, okay, let's just write this down, ICE, at equilibrium the concentration of magnesium was equal to 2.4 times 10 to the negative 4 molar, right? So now this value is also the molar solubility of magnesium fluoride. And what is that saying? That's saying that we needed 2.4 times 10 to the negative 4 moles per, okay, we'll just assume that we're just dealing with moles. 2.4 times 10 to the negative 4 moles of magnesium fluoride to generate 2.4 times 10 to the negative 4 moles of magnesium. Again, we're assuming that we're in a 1 liter solution of water, okay? So that's all it is. So again, to make things simple, whenever you're asked to find the molar solubility, look at your products, okay? Look at your products. Whatever product that has a coefficient of 1 in front of it, okay, the equilibrium concentration of that species is equal to the molar solubility of your starting compound. Well, now it kind of gets tricky. What if you don't have a, what if you didn't have, you know, the products, what if they had like a coefficient of 2 and a 3? There was no 1. So for example, let's just say, let me think, let me see if I can find a, well, this should be one, barium fluoride, okay? So again, we found the molar solubility, and so the solution to the answer, the solution to the question was and is 2.4 times 10 to the negative 4 molar, okay? And that's the molar solubility, okay? That's the molar solubility of magnesium fluoride, okay? And let's look at some other extreme examples. So what if we had, hold on one second, let me see if I can find one. Let's just say we had like something like iron, iron 3 sulfate or something like that. Yeah, so this will have a 2, 3, something like that. Now let's, and this is a solid, right? It's slightly soluble, and will generate Fe2 plus ions plus SO4 3, excuse me, it's 3 plus, and this is 2 minus ions. Again, we want to balance the reaction. And again, for this example that I'm showing you guys, this is just another example. I just want to get down, I just want you guys to understand the concept of molar solubility, okay? So this has a 2 in front of it, this has a 3 in front of it, right, to balance out the reaction. So now let's just say, for example, okay, this is, I'm completely making all this up out of my head, okay. Let's just say at equilibrium, okay, the concentration, we find the concentration of iron to be something like 1 times 10 to the negative 3, right? Or let's just say it's 2 times 10 to the negative 3, and that's equal to the iron 2 plus concentration, right? And the concentration of the sulfate ion will be 3. It will be 3 times 10 to the negative 3, and that's the concentration of it. Okay. So again, your professor gives you an exam and asks, once you find the concentrations of the ions, he asks you what is the molar solubility of this iron 3 sulfate. Okay, iron 3 sulfate. So how would you deal with this? You know, initially in the previous example, I told you guys look for the product that has a coefficient of 1 in front of it, and the equilibrium concentration of that species is the molar solubility of your compound. But what if you have this type of example, or this type of problem where you have a 2 and a 3? There's no 1 coefficient in front of it. How would you deal with this? Well, when you guys were doing the ICE table, to figure out these values, okay, it was initially 0, 0, x, 2x, 3x, and it was again, initial plus the change will be 2x, the initial plus the change will be 3x, right? So we know the equilibrium concentration will be 2x and 3x. So let's just say that we solve for x, okay, and we find x to be equal to 1 times 10 to the negative 3, okay? And that's how you plug this value into here, and that's how you got 2 times 10 to the negative 3. Plug this value into here, and that's how you got 3 times 10 to the negative 3. And your professor again asks you, what is the molar solubility? Well, you can't say the molar solubility is 2 times 10 to the negative 3, nor can you say that the molar solubility is 3 times 10 to the negative 3. It just doesn't make sense. Again, we have to think about this intuitively, okay? So for every iron 3 sulfate, for every one of this compound that breaks up 2 substituents, we generate 2 and 3, right? So we could do a little calculation, but it's easier than that. Whatever x value you get, okay, whatever x value you get from doing the calculation, whatever calculation you did, that is another way to determine the molar solubility of that compound. Okay, so what is it saying? Let's just say we have this is a very easy way. This is an easy way to look at this problem. So we're saying that, for example, we have 1 of this compound. For every 1 of this compound, we generate. So for every 1 Fe2 SO3 we generate 2 Fe. Okay, let's look at this right here. So for every Fe2 SO33 we dissolve, we get 2 Fe3 plus we get 3 SO4 2 minus, right? That's what we get. So in the same, like similarly, we're going to do the same thing. For every 1 times 10 to the negative 3 of this compound that dissolves, we get 2 times 10 to the negative 3 and 3 times 10 to the negative 3. Again, we generate 2 times that amount and 3 times that amount, and that's exactly what we did. This is the value we had that dissolved, and we generate 2 times this amount and 3 times this amount over here. Okay, so again, if you can figure out the x value, you know, I'm dwelling a little bit too much on this concept, because the only reason I'm dwelling on it is because a lot of people get confused with these types of problems. Again, there's 2 ways to determine the molar solubility. One way is if you find if your product, one of your species in your product has a 1 for the coefficient, the equilibrium concentration of that species is the molar solubility, or whatever x value you generate, that is also the molar solubility of the compound. Okay, so that's that. Okay, hope I didn't confuse you guys with this. Okay, because a lot of people have troubles with understanding molar solubility. Okay, and the other question was asking how many grams of the magnesium fluoride dissolves to generate that equilibrium concentration of magnesium and fluorine. Well, we determined that at equilibrium, the molar solubility. Okay, so let's write that down. The molar solubility was equal to 2.4 times 10 to the negative 4 molar, right? Moles per liter, right? So how many grams of this magnesium fluoride, okay, this is again referring to magnesium fluoride. So again, how many grams of this magnesium fluoride dissolves in 1 liter? Okay, so all we do now is we'll start off. We have 1 liter. Okay, that's what we're trying to determine. What is the molar? How many grams dissolves in 1 liter? We multiply it by the molar solubility, which is 2.4 times 10 to the negative 4 moles per liter of magnesium fluoride. Okay, and then we multiply that by the molar mass. Okay, 1 mole of magnesium fluoride. Let's see, what is the molecular weight? It is 62.3, I believe, grams of magnesium fluoride, and it's equal to, let's calculate this, so 2.4 times 10 to the negative 4 times 62.3 is equal to 0.015 grams of magnesium fluoride. Okay, so that should make sense. Okay, so again, we start off with the volume that we're asked. So it's asking how many grams of magnesium fluoride dissolves in 1 liter of water. So 1 liter of water times it by the molar solubility, right? And then we get the moles of magnesium fluoride. We multiply by the molar mass, 1 mole of magnesium fluoride, and the weight, which is 62.3 grams of magnesium fluoride. It gives you 0.015 grams of magnesium fluoride. Now, let's just say, what if the question was, how many grams of magnesium fluoride dissolves in 5 liters? Okay, so before we get into the calculation, let's think about this. If we have more water, the most reasonable guess would be that it would dissolve, more of it would dissolve. So let's see what would happen. 5 liters. Again, let's think of another example. If we have sodium chloride, if we had salt and we dumped it into some water, right? If we keep dumping salt, let's say into a cup of water. I like to make a little picture because it's important to understand this instead of just cranking out numbers. Anybody could do that, but understanding it is a whole other thing. So we add salt. We're adding salt, NaCl. Okay, so we're getting, and these dots represent Na ions and chlorine ions. Okay, so the larger dots are Na ions and the smaller dots are chlorine ions. So we're getting more and more and more ions, and we're dumping this into some water, right? Eventually, when we dump too much, it becomes saturated. It just gets so packed with sodium chloride, this little cup of water, that we start to develop just a chunk of sodium chloride at the bottom, and it starts to get larger and larger, and it reaches its capacity, and it cannot dissolve anymore. So we start to get just a clump of sodium chloride, and eventually no more dissolves, and we're just left with sodium chloride. And it's mainly due because we don't have, this phenomenon is due because we don't have enough water. Now if we expand this, okay, if we increase the amount of water, we made it like this, now we can have more sodium chloride dissolve. And that should make sense. You guys can do that at home if you guys don't believe me. So that should make sense intuitively. Okay, so our guess is that if we have 5 liters, we should dissolve more magnesium fluoride. I'll continue this problem in the next part. Okay, so stay tuned. So welcome back, everybody. We're dealing with what if we had 5 liters of water? How would things change? Okay, we guessed that if we have more water, more of it will dissolve. So let's see what happens. Okay, and we looked at sodium chloride as an example. Again, we multiply this by the molar solubility. Magnesium fluoride. The molar mass, we multiply by the molar mass, 62.3 grams of magnesium fluoride. 1 mole of magnesium fluoride. Okay, now let's see what happens here. 5 times 2.4 times 10 to the negative 4 times 62.3 is 0.07. Hey, check that out. Our guess was correct. 0.5 grams of magnesium fluoride. Everything works out perfectly. So by increasing the amount of water, okay, by increasing the volume, we just increased the potential amount of magnesium fluoride that we can dissolve. So we can dissolve 0.075 grams of magnesium fluoride in 5 liters of water, compared to 0.015 grams of magnesium fluoride in 1 liter of water. Okay, so there you go. So let's move on to the next part. Okay,